Area enclosed by a curve and a line. Now we've looked at how to find the area under a curve by using integration and then substitution in two limits. Now what we're asked to do here is we're asked to find its area enclosed by the curve and this line. Now the curve has the equation y equals 7 minus x squared, and the line has the equation y equals x plus 5. Now to find this section here, this shaded section, what we need to find is we need to find the area under the entire curve between the 2 points there and there, and we also need to find the area underneath the line between those exact 2 points, and then subtract the two areas away to leave us with the bit enclosed. Now to do that we need to obviously discover what the value of this point here is and this point here. So to do that we need to set the two y equals 7 minus x squared and y equals x plus 5 equal to each other. So we're going to set y equals 7 minus x squared equal to y equals x plus 5. So that's going to be 7 minus x squared equals x plus 5. And to solve this we want to collect all the terms on one side and then set equal to 0 so we can solve the quadratic. So the easiest thing to do is to bring this minus x squared over to the other side by adding x squared to both sides. So we can have 7 equals x squared plus x plus 5. Now we need to subtract 7 from both sides to make this quadratic equal to 0. So x squared plus x minus 2. Now that does factorise quite easily into x plus 2 and x minus 1, which means the two x solutions are x equals 1 and x equals minus 2, because remember we're looking for the value that makes each bracket equal to 0. Now we may want to find the coordinates for these points to help us later on. So we know the x part is 1, so to find the y part we need to substitute our x values into y equals x plus 5. So y equals 1 plus 5, which is equal to 6. So one of the solutions is 1, 6 where the curve and the line cross, and the other one is going to be y equals minus 2 plus 5, which is equal to 3. So the other value where they cross is minus 2, 3. Now we know where the two solutions intersect or cross. We can now go ahead and find the area of this section here, and we can also go ahead and find the area under the curve. So firstly, let's look at finding the area of the blue section that I've just coloured in. Now if you look carefully you should notice that this shape here formed is actually a trapezium, and at GCSE you learned that the area of a trapezium was equal to A equals a half of A plus B multiplied by the height. So we're finding the area of the trapezium at the minute. So we need to know that the A and the B are, which are the two parallel sides. So if we look at our diagram, the two parallel sides are this and this. And if we just write down the two solutions or coordinates that we've just found, we found that this one was 1, 6, and we found that this one was minus 2 and 3. So what represents the parallel lines? Well, for this one here, it is the y coordinate, which is the 6, and for this one here, it is the y coordinate, it is 3. So our two parallel sides are 6 and 3, and then we need to find the height between the two, which is the difference between minus 2 and 1, which is 3. So our A and our B are 3 and 6, and our height is also 3. So the area for the trapezium is 9 times a half, which is 4.5, times 3, which is 13.5 units squared. Because we have no units, we put units squared. Now, the other thing we need to find is we need to find the area underneath the curve. Now we know the two limits are going to be 1 and minus 2, and we're not going to have to worry about having any negative areas because we are looking at the section underneath the curve, enclosed between the curve and the x-axis. So we're going to integrate our curve between the regions mentioned. So we're integrating between 1 and minus 2 of 7 minus x squared dx, which leaves us with 7x minus a third x cubed between 1 and minus 2. And that is going to find us the area for the section underneath the curve. And if we substitute in that 1 and minus 2, we're going to get the following. We'll have 7 times 1 minus a third times 1 cubed minus 7 times minus 2 minus a third times minus 2 squared cubed, which we sort out that answer, we end up with 18. So finally, our area enclosed between the curve and the line is our area under the curve subtracted our area underneath the line, and we end up with a final area of the enclosed section as 4.5 square units. Our second example, the diagram shows a sketch of a curve with the equation y equals x in bracket x minus 5 and a line with the equation y equals 4x. Find the area of the shaded region. So the first thing that we need to do, yet again, is we need to find the point at which our two things intersect, which are here and here. So to do that, we need to set y equals x minus 5 equal to y equals 4x. So x minus 5 is equal to 4x. Now we need to probably expand this left hand side here to get x squared minus 5x equals 4x, and if we collect all the terms on the left hand side we get x squared minus 9x equals 0, and we can factorise this to x and x minus 9. So our two solutions are x equals 0 and x equals 9. Yet again, it would probably be a good idea to find out what our y components are. So if we substitute them into y equals 4x, 4 times 0 is 0, so that's one solution is 0, 0, which you can see from the sketch, and y equals 4 times 9, which is 36. So the other solution is 9 and 36. Now this time we're asked to find the enclosed area here. Now it's slightly different to the last example, because if we find the area under the curve between that point and that point, we're going to have this section here, which would be a positive solution, and we'd have this section here, which would be a negative area. So we'd actually have to do it in two separate parts. We'd have to integrate between here and here to find the area I've just shown you, and between here and here to find the area here, and add them together. And to find the area of the triangle, well, we only know that. We could find that length there, but we wouldn't know that bit. So that'd be a little bit more difficult. However, there is quite an easy solution for figuring out how to find this area. Because if we look at this section here, what we form, if I just draw on that line I've just drawn, we form a right angle triangle. where we know that distance there because we've just found it, because that's 0 and that's 9. 0 and 9. So we know that the base length there is going to be 9, and we know the height because we've also just found it for that distance there, it's 36. So we can find the area of a triangle by doing base times height divided by 2. So let's just find the area of the triangle. Area of triangle, which is equal to 1/2 times 9 times 36, which is equal to 162 square units. Now we can also integrate the curve between the two solutions here and here, because if we integrate it between there and there, the area is only going to be positive. Well, we know that entire area there is 162. Well, if we can find that area there, which we can do, because we know that point there is 9, and we can find that from just looking at our original equation, which tells us that our quadratic crosses the x-axis at 0 and 5, we can find the area of this section and subtract it from the area of a triangle, just to leave us with that section there. So we're going to integrate our original y equals x in brackets x minus 5 between the limits 9 and 5. So we're going to integrate between 9 and 5 x minus 5. Now we need to expand the bracket first to just help us with that integration. So that's x squared minus 5x dx. So add 1 to the power and divide by the new power, minus 5x squared over 2, and our limits are 9 and 5. We now substitute in our values. We're going to have 9 cubed divided by 3 minus 5 times 9 squared divided by 2 minus 5 cubed divided by 3 minus 5 times 5 squared divided by 2. And if we find out what these two bits are equal to, the first one is here is equal to 81 over 2, and the second part here is equal to minus 125 over 6. Well, a minus becomes a plus, so the area under the curve is 184 divided by 3. So now we know that this section here is 184 over 3. We know that the area under the triangle is 162 square units. So the final area of the orange section is going to be, so total area is going to be 162 minus 184 over 3, and that is equal to 302 over 3 square units. Now, in an exam, make sure you use your calculator to not make any silly mistakes with your fractions, and also just recheck you've done all your substitution correctly, because it's quite easy to make silly mistakes on questions to do with areas between a curve and a line.